You have in your possession two rectangular bars. Each of these bars is 30 centimeters in length and has a square cross section of 2 by 2 centimeters. The first bar is made of steel with a thermal conductivity of 40 watts per meter Kelvin, and the second one is made of aluminum with a thermal conductivity of 200 watts per meter Kelvin. You decide to do two experiments in heat transfer as shown in the figure below. In part A, we're asked to find the total heat transfer rate H for experiment A. Part B is the same for experiment B. And in part C, we're to find the temperature at the intermediate point where the two bars connect during experiment B. All parts of this problem deal with heat transfer, for which most textbooks use the letter H. H is not a quantity of heat in joules, as is the variable Q, but instead H is a rate at which heat transfers from one place to another, and so it is a heat per second, joule per second, or more simply in watts. What we find is that if the heat is transferred by conduction through a solid, liquid, or gas, we have a parameterized formula that tells us that the heat flow is equal to the thermal conductivity times a few geometrical factors. The heat flow is largest with a big area, and it decreases as the length of the bar increases. And finally, the heat flow is related to the difference in temperature between the two ends. This formula will be applied in both experiment A and in experiment B. Looking closely at these two figures, what we recognize is something that may be familiar to people who have studied electrical circuits. In experiment A, heat flows in parallel, both through the steel and the aluminum bar, and in experiment B, the heat flows in series. Part A of the problem deals with the heat transfer in experiment A, and what we recognize is that the heat will transfer both through one bar, and we can call the heat transfer through there H1, and through the second bar, where we'll call that heat transfer H2. What we recognize is that the total heat that is flowing in from the left splits, sending a certain amount H1 through one bar, H2 through the other bar. So what we'll find in this problem is that H total will be equal to the sum of these two heat flows, H1 plus H2. Each of the terms, H1 and H2, are given by the same formula. In the first case, we'll have a thermal conductivity of 40 times an area. The area is the cross-sectional area of the bar, which will be 0.02 by 0.02, since it's a 2 by 2 centimeter bar, divided by the length of the bar, which is 30 centimeters or 0.3 meters. Finally, the first bar has a temperature difference of 100 minus 0, where I'm taking the higher temperature end minus the lower temperature end. The second term is exactly the same, with the exception that the thermal conductivity that we use is 200 for an aluminum bar. It conducts heat much better than steel. And so we find that there are no unknowns on the right-hand side of the equation, so we can simply plug in these numbers to yield a total heat transfer rate through experiment A of 32 watts. In part B, we're asked to calculate the total heat transfer for experiment B. Let's look a little more closely at the figure for experiment B. We can imagine some total heat, H total, is flowing in from the left. Since there's nowhere else to go, the heat flowing through the first bar, H1, must be equal to the total heat, H total. And again, at the junction between these two bars, the total heat flow in must equal to the total heat flow out, so that H2 is also equal to H1, which is equal to H total. The one thing that's not labeled at this figure is the intermediate temperature, which I'll call by the label T. To solve this problem, we need to express what we just stated in an equation form. What we have stated is that H total is equal to H1 and is also equal to H2. Let's write that formula now. The total heat flow through the entire system in part B is equal to the heat flow through the first rod and is also equal to the heat flow through the second rod. We'll plug in our heat flow formula into all the appropriate places. For the first rod, this will be a thermal conductivity of 40 times an area of 0.02 by 0.02, a 2 by 2 centimeter rod, whose length is 30 centimeters, and whose temperature difference, taking the hot side minus the cold side, will be 100 minus T. When we do the same expression for the other rod, we will first change the 40 as our thermal conductivity to 200 because we're dealing with the aluminum. The areas and lengths are the same, however the temperature difference is not. In this case, again taking the hotter side minus the colder side, we will have T minus 0 degrees for the aluminum bar. Initially, let's look just at the second two terms in this triple equation, which has two equal signs. Comparing these terms, we see that there is only one unknown, and that is the temperature at the midpoint. So in fact, we'll need to solve for that before we can continue. Fortunately, the areas and length will cancel out, leaving us with a very simple formula that 40 times 100 minus T is equal to 200T. We'll bring all the temperature-containing terms to the right, leaving us with 4,000 on the left is equal to 240 times the temperature T, which yields a temperature T of 16.66 degrees Celsius. Notice this temperature is not 50, the midpoint between the two T's. It is in fact much closer to 0 than it is to 100. This is because the midpoint between the two materials is connected by a good thermal conductivity to the 0 degree end, and it's connected by a poor thermal conductivity to the 100 degree end. That's a very nice result, and it is indeed the answer to part C. However, we're still working on part B, and so what we're going to do is we're going to take the part of this triple equation to the left hand of the equal sign, wherein we can see that the total heat transfer is going to be equal to the thermal conductivity of the steel times the area of the bar divided by the length of the bar multiplied by the temperature difference, where we take the high side minus the low side to get the result 4.44 watts. This is a decidedly smaller heat transfer than we had in part A, because we expect that heat will be transferred less rapidly if we put the two bars in series than if we put the two of them in parallel. And so finally, we recognize that we already calculated the temperature at the place where the two bars meet in part C, and that is 16.66 degrees Celsius.